All right, good morning, everyone. This is the Multipath session. I'm Sanjay Rao from Purdue University. We have 5 exciting talks today, all of them around the general theme of how you use multiple paths to optimize quality. Our very first speaker is Sandesh. He's going to be talking about Converge, a QoE-driven multipath video conferencing over WebRTC. He's a PhD candidate at the University of Colorado Boulder, working with Sang-Tae Ha. His area of interest is network systems in general and developing low-latency protocols for time-sensitive applications. Sandesh is available in the job market, looking for industry research positions, so please get in touch with him if you're hiring. Sandesh?
Thank you, Sanjay. Today I'm going to present our work Converge, a QoE-driven multipath video conferencing over WebRTC. The video conferencing has been the most popular internet application since 90s and has seen a tremendous growth, especially post-pandemic period. There are many reasons that has influenced this growth, one being the computing power of the device or the device coming with multiple cameras that has higher resolution. There are many video applications that are trending now that try to capture best of multiple world where you're streaming not only from the front camera, but also from the back camera that gives the immense interactivity in the video application. The next generation networks promising to provide the bandwidth and the latency requirement for this sort of applications. However, despite of all this growth and requirement, we still see the video conferencing is still suffering. Forget about having multiple streams. We measured conferencing performance over the WebRTC with just single stream. As you see that, we suffered the frame rate dropping as low as 2 and the latency increasing as high as 4 seconds. During the time like this, the real-time conferencing is not even possible. So how can we solve this problem? The multipath, where you can use more than one single cellular or Wi-Fi or cellular or multiple cellular, can provide potential solutions. So as we see that, if there is a place where T-Mobile cannot provide the required bandwidth, could be compensated by Verizon. Or if Verizon cannot provide the required, then could be compensated by T-Mobile, or place where both of them provide required bandwidth can only lead into a better quality of the video. WebRTC is actually amazing and my favorite real-time communication protocol, and that's supported in most of the devices and most of the browsers. So when we started, we thought, okay, there's a WebRTC, why not build a multipath WebRTC? But also, there are many multipath protocols. There's MPTCP, MPQuick, and MPRTP. So when we initially developed the multipath WebRTC as a part of the Chromium browser, we tested with multiple variants. We were expecting with multipath, whatever the problems were there would go away. And as you see here, as the number of the camera stream increasing, we were hoping with multipath we would get a better frame rate. But forget about the better frame rate, it dropped even below the WebRTC frame rate. Similarly, there were a large number of the freeze duration and extensive amount of the FEC overhead that led to the increased latency. So in the same graphs, you can also see the Converge is providing, that's a multipath WebRTC, is providing the better QoE despite the number of the camera streams. So how did we do that? So mainly we solved the 3 major challenges. Basically, the first one, the scheduler, the core heart of any multipath protocol. We developed it that is actually aware of the video decoding sequence at the receiver. So when the multipath is present, nothing is disturbed at the receiver on purpose. And also, whenever we have multipath, there's a high probability the path characteristics varies over the network that can lead into a very negative impact on the video. So we developed a novel video QoE feedback mechanism that can avoid such distortion at the receiver. And in real-time communication, protecting the packet becomes important. So how do we design a protection mechanism that consider this multipath into the picture? So because we have limited time, I will briefly try to capture the 2 challenges that we solved. Now let's assume that we have 2 paths, path 1 and path 2, and then there is a scheduler that tries to put the packets of this frame. Now, assume the Fi-1 being the key frames and rest of being the delta frames. And if a scheduler does not understand the importance of this key frame or the importance of the types of the packet, it might end up sending the packets of the important frame on a slow path. And as the packets arrive, and if the packet from the slow path is lost in the network, then the packet buffer could get filled. Unlike the streaming application systems, the conferencing system has very limited amount of packet buffers. So the packets from the fast path are coming in and there's no space, which will end up dropping the packets from the packet buffer. As a result, the frames that goes to the frame buffer is a delta frame, and as soon as it realizes that there's a missing key frame, it simply drops the delta frame because it cannot decode it and then request the key frame. And also another important observation here is that as soon as it drops the key frame, it also drops or purges the packets from the packet buffer. The important reason for this kind of design is because in the conferencing, the packet buffers or the buffers are very small in size, and then to retain the time sensitivity. This causes very less number of the frames for the decoder to decoder that eventually results in the stalls in the video. Well, if a scheduler knew that, okay, I have a key frame, and if I end up sending it onto a fast path, all these events could have been easily avoided. Okay. Okay, sorry about that. I'm talking about the conferencing, and then I got stuck with my presentation. So we were in the middle of how the drops happens in the packet buffer and frame buffer. Let's consider another scenario where, now I'll briefly talk about the challenge too. Now, let's say that our scheduler is aware of the importance of the frames or the importance of the packet, and then it decided with the ratio that I'll send the packets in the ratio of 4:2. Well, I'm receiving all the packets in the packet buffer, where you can actually measure how much time you took to gather all the packets of a given frame, or a frame, you can assume that as a frame construction delay. And now the frames are coming into the frame buffer, very good, and we are measuring the interframe delay between the frames. And over the time, when the network characteristics of a slow path changes, the packet could arrive late in the packet buffer, which can lead into significant increase in the frame construction delay. As the frame construction delay increases, the gap between the frames in the frame buffer increases, which means the frame rate is reduced at the receiver side. Whenever we have multiple paths in the network, usually we provide the feedback in terms of the RTCP, but that feedback only captures the path characteristics in terms of the active flow of packets. But however, when the network dynamics changes and then the frame rate is impacted, if there is no feedback telling the sender, hey, you need to limit the number of packets on a particular path because it's impacting your QoE in terms of the frame rate, our receiver feedback will send a new type of RTCP feedback that says, hey, you have a slow path that's kind of creating the blockage in your receiver, and try to reduce the number of the packet on that. So once it receives that feedback, it starts adjusting the number of the packets on individual path and start re-injecting the packet of a slow path into the faster path. Eventually, if we reach a point where we need to disable the path, then we use the feedback where the particular path was throttled with the ratio of 0. We will enable it back with the improved network condition. So in summary, when we built Converge as a conferencing system, this is the WebRTC architecture we had. We added the multiple path support that can push the packets and receive the feedback for the individual packet. And our aware scheduler understand what is the decoding importance and provide a differential treatment to the packets that are coming from the frames that would avoid the decoding sequence. And then we have a QoE feedback that will avoid drop of frame rate or QoE drop at the receiver due to the varying nature of the networks of the paths involved in the multipath. And also, we have developed a FEC mechanism that's actually more path-specific due to time constraint. I'm unable to explain it. And we developed a congestion control that's actually uncoupled in nature, where individual path is treated as a one network path, and we derive the sending rate of each path with the GCC, and then compute the overall encoder rate. We actually measured the performance of Converge in various network settings, and this is one example. As you see in the video with the Converge on the top, we can actually see the smooth play of the video, where on the Verizon network, we can actually measure what is each frame by actually counting the frame rate. Why the Converge does it? Because it aggregates both the path and provides a constant frame rate, and then avoids the increased amount of end-to-end latency. So the goal when we started with the WebRTC, with the Converge, was to support multiple camera streams. So despite the number of increases in the camera streams, like maybe the AR, VR applications, we didn't want the latency to be increased. So as we see from our measurement, the latency is retained and doesn't increase with the number of increase in the camera streams, and majorly that comes from one of the important component, which is the FEC, that actually reduces the overhead and improves the utilization. We also measured the normalized QoE performance. As we see that the converged throughput is almost equivalent to the individual path, and when we measured the PSNR values, Converge provides a better image quality because it uses multiple paths together. So in conclusion, we built a multipath WebRTC as a Converge that works over the WebRTC, and it works with any Chromium browser because we integrate it as a part of the browser, and it actually works on a principle of 3 components: video aware scheduler, feedback mechanism, and path-specific FEC. So with this, we hope to achieve a conferencing where I can talk to my family in India using multiple cameras, maybe standing in the Times Square, capturing best of the both world. And it's also compatible with any device, any browser. With that, I will take questions. Thank you.
Thank you for presentation. So, Quentin de Koning from University of Mons. So that's a nice talk showing the importance of actually correlating your scheduling with your application. And I'm curious, in your case, how different can be your path to make your solution work in terms of latency and your bandwidth? Is it always possible to use multiple paths if they are too different or not? So can you have some insight on that?
If I understand correctly, you're asking, can we use multipath for conferencing irrespective of number of the paths?
Depending on how different are the characteristics of the paths.
So basically what happens in real-time communication is, in the world of UDP, you have a congestion controller that's basically based on the delay and the loss. So if you're using multiple paths, then you need to be aware of the loss and delay, because they are the 2 factors in the RTC, right? So if you can derive somehow for each path what is the loss and delay, and then bring in some of the application context, like in our case, the frame being the important, then we can utilize. But it's especially in latency sensitive application, multipath could lead into very negative impact. Like as we saw when we were starting with the measurement with the initial versions, we only could saw the few frames with a significant amount of freeze. That's because the multipath has the property of the asymmetry or the head of the line blocking. But I have been worked on multipath for a couple of years. I'm a fan of it, but yeah, you have to be very careful with the path asymmetry. As long as you have some sort of feedback telling the sender, or if you're aware of the context, then you can utilize multiple paths.
Okay,
yes.
Thank you.
Yeah.
Hello, Yunzhe from Alibaba. Great talk. I have a couple of questions. The first question is, I'm really interested in, so what will happen if you remove the parse FEC? So what is the performance impact, and will your system still performs good if you remove that part?
So the FVC is only the add-on. So basically what happens, especially in the WebRTC, it uses some sort of static table. So when we enabled the FVC, the aggressiveness was too much. That means the generated FVC packets were more than the media packet. So that kind of led to the lower quality. However, we don't need to do that much of the FVC if we send the packets being aware of what is the path, what is the loss on that particular path, and then compute based on the path for the number of the FVC packet. That way, you do need FVC, but you're not aggressive for generated FVC packets so that your quality is improved. However, to answer your question, if I disable my FVC, I will still get better performance because I'm using multiple paths. We still have the feedback mechanism, and also we have the multiple paths that should give the benefit. In our paper, we actually show the much more detailed component analysis that actually shows what happens with and without the FVC, and we can discuss later too. Yes?
I'm sorry, but we'll need to cut questions off. Let's see if we'll have time for a panel at the end, or you can talk to the speaker later. Let's start. Nikita is a fifth-year PhD student at MIT, working at the intersection. Our next speaker is Nikita. Nikita is a fifth-year PhD student at MIT. He's working at the intersection of computer architecture and networking with Christina Dilimitru, mainly focusing on FPGA SmartNICs. He's also collaborating with Microsoft Azure for Operators, where he works with Anuj Kalia on cloud-native radio access networks. Nikita, please take it.
Thanks for the introduction. Hello, everyone. My name is Nikita. And in this talk, I will introduce our work on Slingshot, a system which enables fault tolerance and live upgrades in virtualized radio access networks. This work was done at Microsoft Azure for Operators in collaboration with Tao Ji from UT Austin and our colleagues from MIT and Cornell University. So as most of you know, cellular networks is the infrastructure which allows our phones to connect to the internet over the air. The heart of every cellular network is called the radio access network, the part which converts signal samples received from base stations into the Ethernet packets and vice versa. So traditionally, RAN is implemented using specialized hardware such as DSP or FPGA. Virtualized radio access networks, or vRAN, is a new concept which implements RAN processing in software, and it can be run in a general purpose data center. So vRAN offers reduced vendor lock-in, rapid feature development and upgrades, and easier maintenance, and potentially lower cost of ownership. So the vRAN market is growing across the world, with, for example, Rakuten already deploying 30,000 units in Japan. So now let's take a look inside a typical data center which runs vRAN. So the data center consists of multiple servers hosting vRAN software, interconnected with the switch. And the switch is also used to connect the data center with the nearest cell sites. One of the biggest issues today with today's vRAN deployments is that they miss resilience, an ability of the system to tolerate faults and undergo software updates. For example, if a server running an instance of vRAN crashes, it will cause all the connected cell sites to go down. The figure on the right shows our experiment with video conferencing running over a 5G phone connected to vRAN deployed with today's technologies. The y-axis shows the achieved throughput, the achieved average video bitrate in kilobits per second, and the x-axis shows the time of the experiment. So as you can see here today, after the server failure, the video downtime is almost 7 seconds until the connection recovers. So such a long downtime is undesired in cellular networks, and it's inapplicable in many applications vRAN is envisioned to be using for. So another scenario for resilience is software updates, which currently require shutting down a set of cell sites for the time of the upgrade. So this picture, this animation, shows a simplified logical view of how resilient vRAN works when deployed with Slingshot. So in short, Slingshot allows vRAN processing to migrate between servers during resilience events. And for example, with Slingshot, our video conferencing never goes down, and its bitrate remains stable through instantaneous failover. So now let's see how Slingshot works. The edge data center runs latency-critical parts of the vRAN, such as layer 1, also known as physical layer of I, and layer 2, which includes media access control layer. So this work is focusing on providing resilience to the VRAN's most performance-critical part, the baseband processing layer 1. So this is a key component of VRAN, which does actual signal processing, such as Fourier transform, error correction, modulation, encoding, and so on, over single samples to transform them into the user bits. So it might seem like VRAN, and in particularly the PHY software, is not different from any other cloud application, and its resilience can be handled with existing technologies. Unfortunately, this is not true. So first of all, PHY is a real-time software, and it needs to do signal processing under hard sub-millisecond deadlines. If these deadlines are violated, the VRAN will lose data or even crash. So we first tried to implement PHY resilience via VM migration, and we found that it takes at least 100 milliseconds of downtime, which is much more than our sub-millisecond deadlines. So another challenge and issue is related to the fact that all existing VRAN infrastructures are often closed source and quite complex, and they are designed to operate over fixed protocols. So basically, a resilient systems must be completely transparent and interoperable with them. This, for example, prevents techniques such as offloading state during migrations into reliable state store. So let's see how Slingshot handles these challenges. The first challenge is how to migrate PHY processing between servers in real time. And our main observation here is that we can actually view baseband processing as a stateless function execution. So let me show it with a quick example. Suppose the PHY receives a bunch of samples to process a time window T1, and during the processing, it will generate some state. Then it gets another samples to process, a time window T2, which will generate its own state. So the observation is that in baseband processing systems, there is almost no dependency between the states in two consecutive time windows. So this means that we can move processing for another time window into different server without introducing much of state inconsistency. So what I mean by almost is that in real baseband processing systems, there is a little bit of state being carried over between the windows. So one example of the state is the average value of signal-to-noise ratio, which is computed across multiple windows. So here we rely on another interesting observation, that such little state inconsistency, they don't introduce more errors than regular wireless environments, which all cellular networks are designed to handle. So this basically means that we can discard the state, and it won't impact performance of the network beyond regular environments. So the conclusion is that we can reduce complex migration with state transfer to stateless rerouting of connections with the PHY. However, implementing this rerouting is still challenging. As I mentioned earlier, today's VRAN statically provision servers and interconnect them in a fixed way. So this fundamentally disallows any flexibility in the system required for failovers. So to handle it, Slingshot introduces two new middle boxes. We first disaggregate layers, layer 1 and layer 2, and allow them to run on separate servers. And this is done in the software middle box, which is also responsible for rerouting connections between the layers, depending on which server is currently active. And then Slingshot also enables a P4 switch middle box, which runs in the programmable switch, which is responsible for flexible rerouting of connections between the servers and the cell sites. This middle box also runs the failure detection program in the data plane. So this picture shows the complete overview of resilient VRAN operation with Slingshot. So suppose the bottom server is currently executing baseband processing for the layer 2 running in the middle server. If it crashes, the P4 middle box detects the failure immediately and commands all other middle boxes to reroute connections to another server. We deployed Slingshot on a production-grade 5G VRAN testbed consisting of x86 servers equipped with 100 Gbps NICs and Tofino-based programmable switch, and we use Foxconn radio units. As the VRAN and 5G core software, we use Intel FlexRAN, Capgemini Altran, and MetaSwitch Fusion Core. And we do end-to-end experiments with a couple of user devices, such as mobile phones and Raspberry Pi boards. So we first show that Slingshot allows VRAN to sustain throughput during resilience events. So in this experiment, we send traffic between user devices and local servers connected via VRAN deployed with Slingshot. And we measure throughput for TCP and UDP. So the graph at the bottom shows the achieved throughput in megabits per second on the y-axis over the duration of the experiment. So we observed that Slingshot enables immediate failover for UDP, and the UDP traffic never goes down. So the TCP connections, however, sometimes experience short downtime. In the worst case scenario, it was 100 milliseconds, and this is related to the way how TCP handles the transmissions. However, this downtime is still much less than 7 seconds without Slingshot, as shown in the beginning of the talk. In the next experiment, we show how Slingshot enables live migrations of the PHY with zero downtime. So this setup is very similar to the previous one, but instead of failover, we do planned update of the system between two different PHY configurations. And the graph is similar. It shows the throughput achieved by 3 different user devices over the time of the experiment. So we first configured, the first PHY was configured suboptimally, which was causing unfair bandwidth balancing between the user devices, with the Raspberry Pi device getting more bandwidth than the phones. And then we migrate processing to another PHY configuration, which enables fair bandwidth balancing. That's just an example. And the most important thing here to note is that with Slingshot, this update happens instantaneously, with 0 downtime of any of the devices. So to conclude, I'd like to say that today's vRAN, they miss resilience, which is a must-have feature for any cloud application. And this work is the first attempt to enable resilience in vRAN's baseband processing. So it's based on the observation that we can actually view the PHY as a stateless function executor and view all the little state inconsistencies and wireless impairments. So basically, we don't need to migrate the state, and the PHY migration can be implemented in a stateless way, therefore satisfying the hard real-time requirements of the PHY. So, and in order to enable resilience transparently, Slingshot introduces 2 new middle boxes. So we demonstrate that our principles work in practice with end-to-end deployment on real production-grade 5G testbed. So this is all for my talk, and I'm happy to handle questions.
Why don't we have this person in the front ask the question? He missed the asking last time. So.
Purey from MIT, so very, very great talk. So I'm curious for the real applicability of this system. Can you comment on the some statistic like mean time between failure MTBF for the non-vRAN and vRAN with your system? Like how this will actually benefit the percentage of the failures. And my second question is like in your results, you show that the TCP are still impacted by the failures. Can you comment on the further opportunities that your middle box can buffer and recover some of those errors, like to avoid interruption of the loss?
Yeah, so I'll start with the second question. So the experiment that we show with the TCP, this is the worst case scenario, and it actually doesn't happen that often. And in this work, we are not focusing on improving this because that was within the reliability target that we were focusing on. But we are still working on we are working improving the system, and in particular for the TCP scenario, that's one of the immediate goals. And the second question, I'm not sure if I understood it correctly, but so currently, for example, when the update happens, like the cell sites, they go. Like the update takes a lot of time. It might take several minutes currently to perform the update. And this is like during this period, the cell sites are currently down. So you can think about it as for transparent updates, we reduce this time from several minutes to completely to 0. Was it what was your question about?
Maybe let's follow up offline.
Yeah.
There's one more question.
Tom from Columbia, cool talk. In lots of areas, there's reasons to drain resources for software updates, like servers or links. So what's different about this setting where your system is needed? That wasn't quite clear to me. Does that make sense?
Can you repeat this, please?
In a data center, you drain servers or links, other resources during software updates because you need to perform these updates. So what's different about this setting that you need a system like Slingshot?
Oh, because during this update, you don't wanna shut down the cell site. You don't want to reduce the coverage. Because the current systems, they statically provision cell sites to servers in one-on-one mapping. Like there is no flexibility at the protocol level. So if you shut down the server for upgrade, you'll have to shut down all the connected cell sites to the server. Like the protocols, they don't have the notion of replication. They don't have the notion of migration. Like in a traditional data center, you can just, I don't know, you can just change IP addresses, let's say, change the routing, and then just do the upgrade. So here you have to shut down because it's not supported.
Hi, Raj Joshi from National University of Singapore. So I just have a question for your TCP migration. So when you have a fault, you take a long time to migrate in case of TCP. And when you have a planned upgrade, the migration is pretty seamless. So what is the difference? How are you actually migrating your TCP socket?
Right, that's also a good question. So when we do planned upgrade, we can actually make sure that we don't lose any, we don't lose any slots of data. Like in VRAN processing has happened in slots. And if you know when you want to do update, you can actually prepare, and you can make sure that you update exactly the slot boundary. You can make sure that you drain the slot pipelines properly between the files, and you can make this migration completely smoothly. You won't lose any single bit of data. Besides for some small state inconsistencies, but you won't lose actual data in the network. But this is not the case for faults. If faults happens, then you lose slot. You lose slot of data. And yeah, and TCP is pretty sensitive to this.
Okay. We'll have to take other questions later. Okay. Let's thank the speaker. Our next speaker is Yunzhe Ni. Yunzhe is a PhD student from Peking University. He's currently working on multipath transport systems in wireless networks.
Okay, thanks for the introduction. Hello everyone, I'm Yunzhe Ni from Peking University, China. Today, I'm presenting CellFusion, a system for optimizing performance of vehicle-to-cloud video streaming. This work is done when I was a research intern at Alibaba Cloud. Okay, so our subject, vehicle-to-cloud video streaming. Where can we find it? And what characteristics does it have? The most common case is live streaming, where users upload a high-resolution video in real time. Like other video streaming applications, this requires a network to have low latency and high bandwidth. A more challenging case is remote diagnostic, where clinicians remotely direct a paramedic to perform urgent treatment to save lives. However, this is not possible if the video is frequently corrupted or stopped due to network failures. Then, we also have the extreme case, teleoperated driving, which remotely overtakes driving for autonomous vehicles when algorithms fail to solve the long-tail doom of today's self-driving. In addition to the requirement of near-zero error rate, we also need to upload video from multiple cameras at the same time. According to our self-driving partners' use case, this would require the network to have a consistent throughput of 30 Mbps and RTT of less than 200 milliseconds, respectively. Currently, cellular networks that promise to provide both high throughput and low latency seems to be the only fit for vehicle-to-cloud streaming applications. However, our road test shows that with higher mobility, the performance of cellular networks is no longer promising. We observe unstable link quality, high delay jitter, and loss rate ranging from 0 to 100% in both LTE and 5G. So, we see by now, cellular networks cannot support vehicle-to-cloud video streaming seamlessly, and in this work, we aim to address this problem. CellFusion is our solution for enclosing the gap between the fluctuating network and the tight QoE requirements. CellFusion embraces the proxy-based architecture to transparently enable multipath for users. To practically address the network performance issues, 4 key components are included in CellFusion. The first one is multiple connections from different carriers. This is essential for overcoming the fluctuating network condition. The second one is a dedicated hardware to accommodate multiple wireless interfaces and offer a controlled software environment for performance optimization. Then, we have a packet aggregator deployed near the hardware to optimize the end-to-end latency. Finally, we deploy customized QUIC-based transport protocol for optimizing performance while using various functional components from QUIC. So, let's discuss more about the design points and why we adopted them in CellFusion. Firstly, we choose to use multiple cellular connections to leverage infrastructure diversity. Consistent with their video streaming performance, we found that weak coverage of any single carrier is common. But by using 4 cellular connections at the same time, we may reduce the percentage of bad coverage for up to 1 magnitude. We also note that we favor multiple cellular carriers over carrier aggregation to connect to as more base stations as possible and survive failures in carrier core networks. Then, we design our own hardware to accommodate multiple cellular interfaces. The benefit is threefold. Firstly, the controlled hardware provides us computation and storage resources that exactly match our needs. Secondly, the controlled cellular module driver offers better stability and essential runtime information for us to perform diagnostics. Finally, given the flexibility, we are also able to manufacture some hardware components like the antenna for further improving performance. Next, we deploy packet aggregators that forwards video traffic to real receivers at a network edge near our hardware. At the runtime, the hardware automatically chooses the nearest edge proxy server to forward user traffic. We know that the proxy-based traffic forwarding architecture often introduces extra latency when the data path is not only best routing path. So, by placing the proxy server near the hardware, we minimize such penalty. Our last design point is that we use Multipath QoE as the base transfer protocol. As a pure user-space solution, QoE is easier to customize and easier to deploy. Multipath QoE also comes with various functional components that we could reuse, including path management, congestion control, end-to-end encryption, and more. This enables us to conveniently embrace the most advanced transport protocol design, both from the academia and the industry. Next, we will talk about our protocol design and show how it improves video streaming performance. Here, we illustrate our challenge in this figure. When using multipath transfer in a fluctuating network, we use redundancy to overcome latency jitter. That is, we send on multiple paths, and the data would be delivered with the lowest delay of all paths used. However, for the bandwidth-hungry video traffic, we also need to lower the redundancy, because redundant traffic occupies the scarce bandwidth, and also we need to pay for every bit we transferred. So, how to achieve low traffic cost and low latency at the same time? Our answer is to deploy, well, the video is not playing, but let's focus on the text. Our answer is to deploy a partial reliable transfer scheme. To deliver the video traffic in real time, unreliable transfer scheme like UDP is commonly used. But in the fluctuating cellular network, lost or severely delayed packets will directly harm the video QoE. So we definitely need some sort of loss recovery. However, we know that the reliable transfer protocol, such as QoE, suffers from the problem of headline blocking. So in CellFusion, we use a partial reliable transfer scheme to perform loss recovery without introducing headline blocking. Our basic idea is that to detect loss accurately, to perform recovery effectively, and to save bandwidth aggressively. To accurately detect loss, we use a playback deadline information from the video application. In addition to loss detection presented by QoE, we also mark some emergent yet not act packets as lost to perform recovery based on the application's need. Then, to effectively perform loss recovery, we use network coding to withstand the high and varying loss rate and recover almost all lost packets in a single RTT. So, what is different of network coding? Traditionally, the loss recovery would not complete before every packet, at least one redundant copy, is delivered. This scheme is sensitive to repeated loss because lost packets could not be alternated by other packets. However, network coding enables each packet to contain information about all lost packets, so the lost ones could be alternated by other packets. With enough encoded packet received, all original packets could be decoded, completing the recovery. So this is a major point. Network coding-based recovery is more effective because it does not require any specific packet to be successfully delivered. Then, to finish our design, we discard ancient packets that would not be needed by the video playback, and also we only perform recovery once for each packet. In this way, we save the bandwidth and avoid the header-line blocking. We omit many details in the paper, and please feel free to refer to the paper. After the design part, let's briefly go through the evaluation results of CellFusion. In our road test consisting of over 5,000 kilometers of driving, we found that CellFusion outperformed all other comparative solutions on QoE metrics, including FPS, stall ratio, and SSIMA score. From our real-world deployment, we collect packet-level performance metrics to show CellFusion's benefit, since we do not have access to our users' video application. CellFusion significantly mitigated the long-tail effect of latency in cellular networks, and our bandwidth saving scheme achieved an acceptable redundancy cost of about 5%. Okay, finally, let's briefly conclude our work. We present CellFusion, our solution to the problem of seamlessly delivering video in the fluctuating cellular networks. Also, we combine network coding and our partial reliable transfer scheme with QoE, resulting in a practical transfer protocol with best effort reliability, low redundancy cost, and high compatibility. Moreover, CellFusion went beyond research efforts, and our solution is currently working in real auto-driving vehicles to make their decision-making process easier. We believe that CellFusion is a steady step towards teleoperated driving and more amazing vehicle-to-cloud streaming applications in the future. Okay, thank you for listening.
I'm Sandesh from University of Colorado Boulder. So you're using the QuIC protocol at the transport layer, and the QuIC already solves the problem of the HOL problem, which is the head of line blocking problem, because it offers multiple streams within the connection, right? Okay. And you mentioned something about the hardware that is actually reordering in the cloud side. So how much of reordering do you really need? Because the whole point of using the QuIC is to solve the HOL problem. And when you have multipath, the HOL gets severe, but that should be compensated by using a MP QuIC protocol, right? So why do you actually really need a lot of buffering at the hardware level? And in the sense of, I mean, you're doing in the, like...
Okay, firstly, I'd like to mention that we are using a dedicated hardware not for buffering. Instead, we are using this box to accommodate multiple cellular interfaces, because we do not have a like 5G module that can connect to 2 base stations and 2 carriers at the same time. Yes, and QuIC do not introduce any sort of buffering, and in our work, we simply forward you the traffics. Yes.
Okay, and another question.
You should probably follow up with others.
Hi, this is Chung-an. I'm from Toyota Motors. Thank you for the great talk. I have a question about the packet loss and the evaluation condition. In my understanding, the packet loss depend on the connected car speed and the roadway conditions. In your evaluation, what is the vehicle's speed and the road condition? Is highway or the urban or some other?
Okay, we are performing our evaluation in Hangzhou, the Chinese city. It's a very large city. And we are performing our evaluation in urban area. We are driving in about 60 kilometers per hour. Yes, the speed, yes. And well, I'd like to mention that if you use cellular very frequently, I mean, if you set up a very long TCP connection on the cellular interface, like 5 hours or longer, you will frequently observe the latency jitter and some sort of packet loss that what word? That may make your connection break for a while. Yes, even for the non-mobility cases. I'm sorry. Yeah.
Okay. Let's talk about it later. Thank you.
Yes. Thank you.
Yeah. Let's thank the speaker. We have 2 more talks to get through. So next speaker is a distinguished member of the SIGCOMM community, David Wetherall, and he is a distinguished engineer at Google, where he works on low-level networking problems.
Thanks, Sanjay. You're very kind. Actually, it's nice to be here. I haven't been here for a while. Okay, so hi, folks. I'd like to tell you about how to improve network availability with protective reroute on behalf of my co-authors here. But first, a summary, a bottom line summary. PRR hosts use the IPv6 flow label to access working paths. The techniques for doing this have been known for a while. We've extended them. We didn't invent them. But I think people don't realize just how general and powerful they are. Within Google, inside our networks, we use PRR, we use these techniques for essentially all of our traffic, and we have for several years now. We find it to be very simple and efficient, and broadly applicable to many different kinds of traffic and transports, easy to deploy, and that it's able to remove most of the outage time that remains after routing solutions. All of this without any significant downsides. So we hope that you'll consider using these ideas in your network. You should consider them. So the motivation for our work is network availability. High availability is a key consideration for network operators, and particularly hyperscalers. But in this talk, rather than focus on keeping the mean time between failures high, I'm going to focus on keeping the mean time to repair low. And that's because, in practice, our experience is that MTTR is the limiting factor in achieving very high levels of network availability. The classic repair strategy is to use routing in a network which has physical redundancy. So that way, when a link fails, the network is able to find a path around it, move traffic onto it, all without involving the hosts. But routing alone isn't sufficient to achieve very high levels of availability. Routing doesn't handle some kinds of complex faults, particularly when there are interactions between hardware and software. These faults are rare, but when they happen, they result in long outages because high levels of recovery are needed, all the way up to operator intervention. These are the kinds of faults that you read about. More surprising is that routing isn't fast enough for common faults like simple link cuts. And the reason is that when local repair mechanisms like fast ReRoute will often fail. They might fail because there's no pre-computed backup path available, or there's too much congestion when it's used. And in this case, you need to fall back on global repair mechanisms, and they tend to be slow in large networks. Instead, Multipath provides an opportunity for faster repair. So modern networks scale their capacity by adding more links in parallel. So you can see between these sites, there are many links rather than a single fast link. ECMP is then used to distribute different connections or transport flows across the many paths through this network. Now, the same links that you add to scale capacity also introduce physical diversity, which means they can fail independently. So in a well-designed network, it's often the case that hosts have working paths, some working paths, to all destinations, even when there's an outage. This means that we don't need, in those cases, to use routing to find new working paths. We simply need to shift the traffic onto the paths which already work, and that restores connectivity for users. PRR uses the IPv6 flow label to access a multipath. So with traditional ECMP, each TCP connection is fixed to a single path. That's because the host can't change the path without changing the ports or the IP addresses that define the connection in the first place. With PRR, we add the flow label to the ECMP hashing configuration at switches. So this means that a host is able to repath an individual TCP connection simply by changing the flow label. To complete the design here, PRR uses TCP events to trigger repathing. So consider this example connection. It takes some path through the network. When there's a black hole in the network that affects the connection, the packets will be discarded in the network and connectivity will be lost for the connection. After a short time, the sender will time out and retransmit. At that time, we change the flow label. This functionality is already there, it's been there in Linux for a long time, actually. When we change the flow label, the connection will take a different path through the network. In this case, it happens to bypass the fault, it's received at the other end, and we use the reverse path that already works, so connectivity has been restored. More generally, there's a set of events at which we can trigger repathing. These include things like duplicate data reception to repair the reverse path, as well as SYN timeouts and retransmissions to protect connection establishment. Often it's the case that simply a single repath will repair connectivity, as in this example, but if it doesn't, then the sender will time out again after a short interval and will try again with a different flow label, and this process will continue until connectivity is being restored. It's a little more involved when there are also faults on the reverse paths, and you can see the paper for details. But all of this repathing happens as host local behavior, which aims to improve on what's going on with routing and traffic engineering, and all of that happens independently. So how well does it work? Let's look at an example of a major outage on our B4 backbone. The graph here shows the loss on the y-axis between affected network regions over time. And you can see here the red line for the network line, or level 3, shows that this was a large outage. It lasted 14 minutes. It couldn't be repaired by routing alone. And during this outage, you can see at least 5% of the connections were black holed inside the network. If we look at L7, this is for an RPC user using existing transports on top of it, they see a reduced outage. And that's because the RPC library reconnects failed connections after 20 seconds or so. And there's churn there as routing moves things around and breaks connections and so forth. So they see a definite improvement, but still a significant outage. This is what you see with PRR. It restores connectivity in seconds. In fact, you have to zoom in to really see what's going on with the repair. So as far as most users of the network were concerned, they were not aware of the outage, except possibly for a reduction in capacity in the network during the time the physical fault existed. To gauge the overall effect, how much it helps with network availability, we ran a 6-month study on both of our backbones, our B2 and B4 backbones, looking at all outage time across all pairs of network regions. This graph shows the reduction in the total outage time. The red bars there are showing you the difference between L3, the underlying network layer, and an RPC user at L7. So you can see that existing transports and RPC systems are able to remove some of the outage time. When you add PRR, PRR then removes most of the remaining outage time. It's gone as far as users can see. And in combination, these two effects mean that users only see a minority of the actual outage time on the network. PRR also has great deployment incentives, given that you're already using IPv6. It's incrementally deployable, so you can upgrade senders, receivers, and switches in any order without constraint. And as I've mentioned, Linux TCP has already been upgraded for a long time. The partial rollout of PRR also delivers very good benefits. This is because if you can change the path upstream of a fault, you avoid a downstream issue. This also means that you can work across multiple networks. An upstream provider is able to avoid some issues in downstream networks using this technique, which is very valuable. So far, I've talked about TCP to give you a concrete example, but it should be clear that these ideas apply much more broadly to any unicast transport. All you need to do is in the transport, when you recognize there's a connectivity issue, change the flow label. That includes multipath transports, by the way, where you're concurrently using multiple paths. You can add the PRR technique to the multipath transports to help protect connection setup from problems, as well as to protect against the loss of all subflows. So you don't need to use a multipath transport for reliability reasons. It also works with a variety of other situations, including tunnels. So for instance, PRR is deployed and protects Google Cloud traffic. All you need to do here is propagate the repathing signal to the outer tunnel headers, and so on. So in conclusion, just to wrap up, I hope this talk has helped you to change your view of how we might design networks for high availability. We believe in using the IPv6 flow label for ECMP. This is the intended IPv6 architecture and has the benefit of letting hosts have some degree of control over paths. We use routing to maintain a diverse set of paths. This causes outages to be only partial connectivity failures, not to partition any network pairs. Then you can use host repathing to repair connectivity rather than invest in fast ReRoute or techniques like that. Host repathing can quickly remove most of the outage time. Thank you. Questions? Yes.
Yeah. Ethan Katz-Bassett, Columbia. I think the last time that Dave and I were in a Q&A was when he was on my PhD defense committee, so looking forward to turning the tables here.
Thank you.
Great talk. I was wondering that there was this paper at NSDI 2021 from Fastly on fast path reconnection where they looked for TCP impairments and then balanced the traffic onto another path when they observed that. I don't remember the details of that, but can you talk a little bit about the kind of pros and cons and similarities and differences between the two?
I'm not familiar with the details of the paper you're talking about, so it's going to be hard for me to do that.
Okay.
You want to zoom in on something?
I don't. It just sounded very similar, and so I was just wondering what, had you adopted that same approach? Did they? But it sounds like you just weren't aware of it.
So well, actually, I'm sure we've looked at it. I just don't remember that one in particular.
Yeah.
There are a large number of papers which do load balancing across multiple paths, which are set up on moving things around, right? And multipath transports in general. And I mean, these are wonderful things in many circumstances. But what's here is actually much simpler. This really says, when you have a connectivity issue, try a different random path through the network.
Yeah, so what I remember that approach was it looked for cases when TCP stopped making progress, and then the host would set a bit that would then cause the flow to be load balanced onto a different path.
Okay.
But yeah, maybe afterwards we can chat about it and once you have a chance to look.
That's great. Let me just briefly say, that's great. You should do that. We think the way you should do that is using IPv6 in the flow label, because then it's simple. All you need to do is upgrade the switch configuration in the network. You get a lot of this for free.
Great, thanks.
Thank you.
Hey, Andrew Redman from Jane Street. Great talk. Quick question. You mentioned tunneling. Any experience with 4 and 6?
No. So we're primarily looking at IPv6 here.
So 6 and 6 only?
Yeah, well, you can protect IPv4 traffic 4 and 6 because if you can recognize at the sender and propagate the signal to the tunnel. What you can't then do is propagate anything elsewhere inside the network, right? But it can work for some IPv4 source traffic too.
Got it. Thank you.
Okay. We need to switch laptops.
Hi.
Maybe we can squeeze in a question while we switch laptops. Okay.
Okay.
Great talk.
Thank you. Question?
Hi, Tom from Columbia. You mentioned that this would work in I think you said a well-designed network. Can you comment on what you mean by that?
No. Well, that might take a little more elaboration than we have time for. But just because you have, so in a well-designed network, you need to make sure that you don't have any single point of failure, right? You don't want a single fiber cut, for instance, to take out all of the different links. They might have looked like parallel logical links, but if they all ran through the same physical place and they're all subject to one cut, you wouldn't get the benefit of sort of the independent failures. And that applies in other ways too. You need to think about all of these factors when you design the network. Try and avoid single points of failure. That's what I mean. Thank you.
Okay. Let's thank the speaker. I need to present presentation on. No, leave it in presentation. Go to presentation mode.
I can leave it in presentation mode.
We're not seeing anything. Let's make sure this works right.
Our last speaker for the session is Bingyang Wu. He's a second-year PhD student at Peking University, advised by Xinjin, and his research interests include machine learning systems, video conferencing, and cloud computing. Please go ahead.
Hello, everyone. I'm Bingyang Wu from Peking University. I'm glad to share our work, XRON, a hybrid elastic cloud overlay network for video conferencing at planetary scale. This is a joint work of Peking University and Alibaba Cloud. In recent years, video conferencing has become increasingly popular and important in our society. Many video conferencing applications have been widely used in people's daily life, such as Zoom, Teams, and DingTalk. As one of the largest video conferencing services in the world, DingTalk serves over 500 million users. Most of our top-tier business customers rely on our service to host international online meetings for regular cooperation management and various business events. To provide planetary scale video conferencing services, DingTalk deploys software in multiple cloud regions of the public cloud without building hardware infrastructure in each nation. This approach accelerates the expansion of DingTalk for cross-region video conferences. Multiple clusters transmit video streams with each other. In this case, the quality and cost of the network are two key considerations for planetary scale video conferencing services. However, simply using resources provided by the cloud platform cannot meet the requirements of video conferencing. The cloud platform provides heterogeneous network resources, including internet links and premier links, but they are imperfect. Different from traditional on-premise deployment, network usage on cloud platform is priced based on product or egress data volume and unit egress fees. Internet links are cheap, but they are unstable due to their best effort nature. As shown in the figure, the loss rate of internet links can be as high as 30% and is much higher than that of premier links. As a latency-sensitive service, a high loss rate greatly impacts the fluency of video conferencing. Premier links can provide high performance for video conferencing, but are too expensive to afford. The unit egress fees of premier links are significantly higher than those of internet links. Therefore, it is challenging for video conferencing to use these heterogeneous network resources. At the same time, unlike traditional on-premise deployment, cloud-native deployment has to deal with the unique elasticity problem. The video conferencing demand is highly dynamic each day. As shown in the figure, video conferencing demand surges multiple times in a day and may increase up to 3 to 4 times in even 5 minutes. In this case, satisfying the stringent stability requirement of video conferencing is challenging. In summary, cloud-native video conferencing makes things different from many prior work. To provide high-quality video conferencing in the cloud, we need to optimize the network in a novel hardware setting to meet more stringent performance requirements at a low cost. To solve these challenges, we propose XRON, a hybrid elastic cloud overlay network for video conferencing at planetary scale. XRON differs from prior overlays with two distinct features. First, XRON hybrid leverages both internet and premier links simultaneously to achieve high quality and low cost. Second, XRON exploits elastic cloud resources to adaptively scale capacity based on real-time demand. An intuitive idea for using heterogeneous network resources is to use direct interconnection between cloud regions with fixed network tier selection. Based on experience, if an internet link between two regions is often unstable, the operator can direct video stream to be transmitted by the corresponding premier links. However, because many internet links are unstable at some unpredictable times, substituting them by premier links still incurs high operation costs. In contrast, XRON applies overlay forwarding for video conferencing. Where network degradation occurs, XRON dynamically combines two cheap internet links to route around the unstable internet links while maintaining low cost. This technique is adopted by many existing overlay solutions, but it increases the RTT of video conferencing. The key insight is that network degradation often only affects one direction of an overlay link in production. The figure shows an example that only one direction of an overlay link has a high loss rate, while another direction is good enough for video conferencing. If simply using the round-trip performance of links to compute the forwarding plan, the solution space is limited and the forwarding decisions are suboptimal. Consequently, XRON class each direction of overlay links separately and use asymmetric forwarding to further reduce the latency and cost of video conferencing. To achieve scalable link state monitoring for the large overlay network, XRON uses a group-based active probing mechanism that combines sampling-based active probing and passive tracking. Please refer the paper for more details. In the end, it works for the long-term network degradation. However, when frequent short-term network degradation occurs, each time media service has to interact with the globally centralized controller to update forwarding tables. It is still slow for latency-sensitive video conferencing. A strawman solution to avoid this is to use naive forwarding plan. When a network degradation occurs, media server can use a predefined path. However, without coordination of the control plane, changing the path may lead to the overlay as a new relay server, which breaks network constraints and experience a longer latency, which brings performance constraints. To handle short-term network degradations, we propose a fast distributed reaction mechanism. The key insight is that the data plane can use premium links without immediate coordination of the control plane. The XRON controller proactively pre-computes and deploys fast reaction plans in the data plane. When network degradation occurs, the data plane of XRON can temporarily use the backup path to circumvent unstable links without involving the control plane. By temporarily leveraging premium links, changing the path does not break the network and performance constraints. As shown in the figure, frequent video conferencing spikes ask for a quick auto-scaling mechanism. Otherwise, it may significantly hurt the performance of video conferencing. However, the traditional reactive container auto-scaling mechanism provided by the cloud platform cannot meet the fast requirement changes. When the traffic demand surges, the capacity cannot increase until a series of slow initialization and checking procedures are done. As a result, users of video conferencing may experience video source and bad audio fluency. Our key insight is that the traffic demand conforms to users' regular daily routine. The video conferencing demand surges when the work time starts and falls back when the work time ends in the morning, afternoon, and night. The figure shows an example. Because video conferencing is mainly used for daily or weekly meetings in the company and scheduled online classes in the school, we can accurately predict the video conferencing demand in the near future. Based on this insight, we propose a proactive auto-scaling mechanism. It uses video conferencing statistics to predict traffic demand and proactively auto-scales containers to co-optimize capacity control and overlay routing. Therefore, XRON can overlap demand changes with capacity control to provide high-performance video conferencing without over-provision. XRON has been deployed in production. Large-scale production deployment shows that, compared to the internet-only version, XRON reduces the video slow ratio and bad audio fluency across cross-region video conferencing by 77% and 65.2% respectively. To conclude, XRON is a hybrid elastic cloud overlay network that combines cheap, unstable internet links and expensive, stable premium links and exploits elastic cloud resources to improve QoE and reduce the cost for planetary scale video conferencing applications. XRON has been deployed in 11 cloud regions across 4 continents to support DingTalk since August 2022. Thanks for listening.
I have a question. Yeah, I have a question. So normally these big cloud providers would have a lot of applications besides video conferencing, right?
Yeah.
So I'm curious why just split video conferencing into premium and non-premium links? How about why not send some of your other application traffic on non-premium links and send all conferencing traffic on premium links?
This work is mainly focused on video conferencing, and we are a user at the cloud platform. Other traffic is not controlled by ourselves.
I see. So you're renting the whole. Got it. Thank you. Yeah.
Hi, Xu Miaozhang from University of Michigan. So I have a question. So you said you do the proactively do the auto scaling. But this is just regarding maybe one time zone. So how about the cross-continent, like cross-country, those conference? So for those scenario, I guess the rush hour or the busy hour will be different. How to consider such scenario?
We predict the traffic demand between any 2 regions, and their prediction is separately. And whatever the 2 regions, our observation is show that there are periodicity pattern.
Okay.
Thank you.
We'll have a short panel. May I invite all the speakers to come over to the podium?
Do I need to switch laptop?
So if you questions, preferably which are for multiple speakers at the same time, that would be preferable. But any question is okay. Yeah, Eddie.
I guess my question is, how often did the multiple pathway thing make things worse? Like where you were flapping between paths? Oh, we've got an answer.
It happens most of the time. If you want to use the multipath, you have to be really, really careful, especially in the video conferencing. I spent multiple weeks sitting in the car, and none of my algorithms were working. But once you have a proper design, it makes conferencing much, much better.
Thank you. My opinion is that multipath works best when you want to aggregate the bandwidth from multiple paths. But if you want to stay synchronized, it is not the best solution. And you must cope with the out of order and many things that make things worse. Yes, that's my answer.
Well, no, I might be a little bit of an outlier here because we're multi-path, but we're not actually using multiple paths concurrently. People did wonder, we did actually consider, flapping around or whatever, but that turned out not to be a problem using a single path and repathing carefully. Thank you, Eddie.
I think there are questions. Venkat, maybe? Yeah.
This question is actually for Dave. With multipathing, or whatever you call it, PRR, is there a risk of causing congestion? Like there's a hot path and you have a bunch of stuff end up on that, it makes everyone worse off, right?
Potentially. So we don't find that to be a problem in practice. Here's one thing to realize though. When I talk about repathing, so when you choose a different flow level, you're very likely to take a different path through the network. But that doesn't mean moving off the point of congestion. So you're not actually flapping between one link. You're not moving everyone from one bad link to another link. That would cause oscillations and congestion, just perhaps as you're asking and Eddie's pointing at. But what we do when we send traffic is you don't know what path you're going to be on. The network is just mapping a flow label to a random draw. So when you try again, you may actually end up on the broken path again. So traffic has been spread, and that spreading process is actually very good at, if you do it over time, at avoiding sort of oscillations or those kind of effects.
I think there was a question. Renata, you had a question? Okay.
All right. Thank you.
This one.
No, I think we need to
call
it. Thank you so much.
Thank you.